the administration. So normally on Wednesdays then we have to be in this R10 room, which was not the best. At least for now. I will tell you as soon as we know something else. On Tuesdays it was then now KL number 5 for the rest of the semester. Come back to if we can find any better room on Wednesdays. I mean, this is quite okay actually, but we'll see. Today we start with more theory on chapter 2. So you have the textbook. I would actually not recommend reading the entire book. It's too many words in my opinion, but at least you have some reference material here. So I'll go through sort of what's important. Also a little bit of programming today, but not too much. So this chapter 2 also will cover the theory needed to handle exercise number 2, which then will be out shortly. So we start chapter 2. Source and a load. For source, you are talking an energy source, power source. So the figure in the book, very simple. You have some supply. Could be a battery, could be something that produces energy that now provides driving a motor like this. And out of the motor you will have a shaft which then will rotate. But a motor, it does actually two things. One thing is that we can make this axis rotate, but also he has to provide a force. And here, a rotating system, we talk about torque. In Norwegian, moment. As force times the arm. So he produces Greek letter P with a dot above. That's the angular velocity, rotational speed. For engineers, they like to use RPM, rounds per minute. SI units, this will be radians per second. So it's a rotational speed. But he also then produces an M for torque. Don't mix momentum and the Norwegian moment. That's something else. Torque, meaning moment in Norwegian, force times R. Momentum in Norwegian, that is mass times velocity. That's something completely different. So we will now make this picture easier. If you look into a battery, how it's designed, how it actually works, or not to mention inside a motor, it's very complex indeed. We are frankly not interested in the details here. So we do the following. We just lump this together and say, this is my source. Sort of a black box. I don't care what's going on inside there. I'm only interested in what happens through this port, where now my source will provide me with rotational speed and torque. So here we call this one a source. How much energy will this source give us? I mean, this rotating axis is now hooked on to a system which I haven't drawn to the right. It can do a lot of things. drive a car, a bicycle, set a van in rotation, I don't know, something. But how much power, how much energy per second goes out here? Well, power, we use a large P for power. That is, okay, how can you get power if you have these two? How can you get power? What's the SI units for power? Well, that's watt, that's joule per second. So how can we get power? Well, you simply multiply these two together. So in order to actually do something, to do some work here, you need both rotational speed and torque. Just one of them doesn't do anything for you, but the combination, okay, then we are talking power. And here we dimension watt. So we want to do something with a machine. We want something that should rotate. So we go to the shop and we say, I need a source, rotational source. I need a motor with a power supply that can provide so and so many watt. And then the guy behind the counter, he gives you something. Sell it for cheap or expensive. But what he should give you, you should never listen to this sales guy, they always exaggerate. He says, oh, I have a perfect source for you here, it can provide you with 1000 watts, no matter what, which is a big lie. So what you then should get is the following. To get a diagram where they actually have taken this power supply with the motor and tested it in the lab. And here tried with different rotational speeds and then see how strong is this torque now. And then typically what you get is a curve, maybe looking something like this. So here you are talking of a characteristic, the characteristics for the source. Characteristics for the source. So then you can see when you switch this power supply on, and he is going to start to rotate. So initially the speed is 0, it doesn't rotate at all. Then you have this much torque on this axis. And actually on some motors you will find that he is extremely weak in the beginning. So this one may be even close to 0, meaning it can be very hard to get things started. But when he has achieved some rotational speed, then he can be fairly strong. But if he goes too fast, the force, the torque drops and then goes to 0, and then he is weak as a newborn baby. So this is what you should get when you buy a motor with a power supply. These characteristics. Then you actually know the real thing. Then you know exactly how he behaves. And then we can start using it, designing, well, any problem. For this diagram, as the book says, you can flip it if you like. So you have phi as a function of m, or vice versa. It's the same figure, of course, just flipped. But somehow you need this information as a diagram or a table or something from the vendor. Yeah, that's something else. How much power will you now achieve from this source, depending on the rotational speed? Or to say another way, take this this equation here, and then you rewrite it. I want a constant power curve, so that should now be m as a function of the rotational speed equals what? Well, as you see, you just take the power and then divide by phi dot. That's it. So if we had chosen a certain power, P equals some P0, say 10 watt or whatever, we are focusing on just one amount of power, then you just do it like this. And you see this is a curve that is going to be a hyperbola. So this is a constant power curve. Constant power curve. It will be a hyperbola. What's the maximum power this source can provide? Well, you can now play around with different values here, and you get a different curve every time. If you choose a too big a number, you will have a curve going somewhere up here, and you don't hit the characteristic at all. Then you overshoot. This is not possible to get. But what you want is just to touch it here somewhere. So here we have the maximum power curve. Just touch it. At that point, you can get the maximum out of your source. How to find this point? Well, a little trial and error. One way to find it. The book also says something of a graphical method. You can find this curve and then the tangent here. And if you have the correct point, this angle will equal this angle. Then you can find this point graphically. That's one way to do it. Before we continue now with an example here, this sprinkler system, I want to show you an example here. It was very small, wasn't it? That one should be a little bit bigger. Come on. Can you read it? This is one way to handle a real data curve. I mean, you don't have the function for this behavior. It's not a continuous function. So you have it either on as a table with some numbers, or you just have it in the graph. Here I just picked out some points. Some arbitrary points, and then in MATLAB use interpolation So here you see just 4 points along the x-axis, and then the corresponding functional values y, and to produce here a curve with, here I've said well, 300, that's a little too much. Take from 0 up to 190, because that's the span of my x-axis. So you start here with 0 and then 190. And these two vectors here, x and y, they are input into a function called inter P1 in MATLAB. That's interpolation, just a simple function. Y is a function of x, but he will then provide you with the new interpolated values if you provide him with some where you want the data. So here I've done it for an entire table. The large X is now 191 values, then I get 191 values back. If the big X there had just been one single number, you will just get one single Y value back. And then of course we plot both of them so you can see how the interpolation works. So here you have it. And it doesn't look all that stupid. But there's some danger here, some extreme danger. Let's see. Grid on, take that one as well. So you see, we start in point 8 and then we stop at 0 here. So that's okay. But using interpolation, that's more or less safe. Not entirely safe necessarily, depends on how you do it. Here you see I have used some cubic spline, so it's a little curved. If you don't write anything in MATLAB, he will provide you with straight lines. So you have different ways of doing the interpolation. So cubic, if we remove this one, like that, he will then provide us with just straight lines. So that's the default. Now, typically we know that the function should be nice and smooth, not these straight lines with the sharp corners, not so physically. So using cubic or a spline, that's quite okay. Cubic and spline, you don't see much of a difference between those two, I think. Ah, the spline there doesn't look too good, does it? All of a sudden, very, very strange indeed. What is a spline? Anybody know what a spline is? Physically? No? From the old boat builders, they used splines. That is a steel ruler. Don't we have anything here? Well, this one. Not so elastic, a little bit. So they used splines to draw nice and smooth curves. So when they had, they knew that these points should be a member of the surface, okay? Then you take a steel ruler and force him to pass through these 3 points, but you do it in a way that the double derivative is going to be minimized in these points. So that is a spline. So then they could make nice, smooth surfaces. So it's from building ships. But here you see rather nasty behavior. It goes negative first and then he goes up, and that's definitely what I want. So if I want to use a spline, then I need more points. The cubic is a little bit safer. Cubic. So that one I can recommend. But, and now comes the important part, when you jump from interpolation to extrapolation. Extrapolation should be illegal, it's terrible, it should never be used. It's a classical story from Kjell Aukrust, where they were very interested in the old Viking areas. So they wondered how big the Vikings were, how tall they were. So they checked it out from the Norwegian army, and there the soldiers have been steadily growing taller and taller over the past 50 years. So they extrapolated down to the Viking area. So the Vikings, they were roughly 20 centimeters tall. You never extrapolate. It's very, very dangerous indeed. So you can see here what's happening if you go outside your region from 0 to 190. That's my region where I have data. So if we now go to, say, 200, I go outside the region. Then you see he goes negative. That's interesting. A source with a negative power. I would like to see that. So he sort of sucks the energy into him instead. Rather strange. And if you continue, say go all the way up to 300, okay, then things are getting very messy indeed. So don't extrapolate. Or if you write a program and you are in the danger of doing an extrapolation, maybe you are searching for a solution and then in the calculation process you accidentally go outside the range of data. How can you do it? Well, here you have these points inside the program. What you then could do was to add some fictitious points, some additional points. So you're going to have added here another point way over here for 0, and for him way over here 0. And then use linear interpolation. Then you will be fairly safe. Then you won't get this very strange behavior. If you take the linear default interpolation, you see he refuses to go outside. Although here I have asked him to plot all the way up to 300, but he refuses to do so when it's linear. He stops at 190. So I'm not sure even if he gives a warning. Let's see. No, you get no warning. He just skips if you try to go outside, if you try to extrapolate. But if you're using cubic or spline, you're allowed to go outside, but be very careful in doing so. You will get some very, very strange results. So interpolation is a tricky thing, so be aware. You can check MATLAB with this inter P1. You just write doc inter P1, and then you can read a lot how you can use this interpolation. This is something that you have to fight with exercise number 2. Okay? Any questions to this interpolation routine? So I will put out these small programs on the homepage so you can find it there later on. We have an example here, a case study that we are going to look into. Before that, we will sort of rewrite the graphical drawing. So this is now what I have. We have the source. Here, power supply and a motor. We just lump this together and I call it a source, call it an S. Then on the other side here, we will have something that this rotational axis is going to operate on. So here I have something that requires power to be moving. We call it a load for now. And the graphical drawing for this system will now look something like this. That is your first bond graph. So now he represents the power transfer from a source through the ports into the load. We use half arrows, and these half arrows we call a bond. So this one is called a bond, a power bond if you like. And we always use a half arrow. And the reason that we use a half an arrow is the two quantities that is going through this bond is always two. They operate always in pairs to provide or to give power. Here we have the motion, something that actually is moving, the velocity, rotational velocity. He should always be under this arrow, or where you have this half arrow head pointing towards him. The force or the effort should be on the other side. So this is something that we are going to do with not only rotational systems, but any system, any combination that will provide power. So half arrow is a bond, and here is what actually is operating on the bond. The direction for this arrow, that is what we define as a positive direction. Sort of the power is flowing from the source into the load. So we will have later a lot of these symbols and a lot of bonds, and sometimes the bonds, they can go up, they can go down. So there's a question, when they go horizontally, we always use this arrow, half arrow head downwards, but when they go, the arrow go up or down, then it's a question, do you prefer to the left or right? I don't care. That's your call, but always half arrows. Okay, we start up with an example. A sprinkler system. Water sprinkler system. So this is our load. But of course we can rewrite the system a little bit easier, a little bit better. You have here sort of the load only, meaning only the right hand side of this graphical figure, but we can take everything. So then we will start here. Here is the source, and the rotational axis there, entering into the pump here. pump. Now this pump, he will suck up water from a reservoir and then push it all the way up to a sprinkler system, fire extinguish at some height in a hotel or in a tall building or whatever. So now it's a question, how high is it? How strong must this pump be to provide enough water to extinguish the fire? Or how strong is this source? How strong must the source be to provide a decent fire extinguish system? This one rotates, you have rotational speed and you have torque. But the entire bond graph for such a problem will now be as simple as this one. You have a source and you have a load or resistance, if you like, on the other side. But here, of course, we have the entire detail. For the source, that's the power and the motor. We have the characteristics from the shop when we bought power supply and motor, so we know this curve. We know the data here, how he behaves in a torque rotational speed diagram. So no problem with him. What about the L? Well, we make the same drawing from him. Well, he will be quite different. So for this part, this is now what we call the load. We are going to need the same characteristics here as well. So meaning we have to build this and do some experiments, or we can maybe simulate it. Should also be possible. And then we plot our data in the same diagram. Torque versus rotational speed. And now we are talking torque and rotational speed for this axis entering into the pump. So here is our sort of input into the load, into the system here. And then is of course a question, how high is this sprinkler pipes? At what storage will we need this one? So at what floor? So the book operates with 10th, 20th and 30th floor. 10th, 20th, 30th floor. So it's a very tall building, hotel or something. So that is actually the load that is required. And as you can see, for get things started at all, zero rotational speed, we're actually requiring a lot of torque to just to get the pump to go around. And then if you need a lot of water, certain volume flow, 10 liters per second, 50 liters per second, I don't know, then you need a high rotational speed, then you need even more torque to do this. Of course, you will have resistance in the pipe here, and if the speed increases, the resistance is going to increase. And here, they are slightly curved, so it's not a linear connection there. Never mind. So now it's a question, do we have enough power to do this? Okay, then we take our characteristics from the source, we take this curve, and we draw it inside the same figure. And say we start here, go up and down. So these are now 3 different load characteristics. And this one is now my source characteristics. Source characteristics. So now the idea is the following. Everything initially is at rest. We haven't switched on the power supply. Nothing is moving, and the pump is standing still. Then somebody detects a fire, and we hit the on button on the source. And then hopefully things should start to move, and the fire should be extinguished. What's going to happen? Say you are on the 10th floor. The fire starts at the 10th, in the 10th floor. So then it should be okay. You switched on the source, and we start everything at rest, no rotational speed. This is the requirement from the load to get things even to start to move. This is what the source can provide us with this torque. Yes, it is bigger than the load. This looks promising. He will start to move. So yes, we will increase the rotational speed. And here the torque is bigger than the load. So as long as the red line is above the white one here, he will continue to accelerate up the system. It will rotate faster and faster until you hit this point. There you are in balance. Then the entire amount of energy or power that the source can give out will be swallowed by the load. So here we are talking about an operating point. Operating point. Of course, for the 20th floor, yes, we have a couple of operating points here as well, where source and load are in balance. But you see, for the 20th floor, we have a problem. It won't even start. When you switch on the power supply, everything is at rest. This is the amount of torque the motor can give, but this is the amount needed to get things to move. And you see, it's too weak. So nothing is going to happen, well, except that you burn up your motor probably. So this is a very, very bad idea. If we could get past the first operating point, then it would be okay. Here, our motor is strong enough. So then we could accelerate, reaching this operating point. That would be okay, but no, you can't even get things starting here. Big problem. So we will then now see how we can remedy that. Any questions?